Alright, Advent of Code Day 8. I'm gonna take a moment to read this and then we can have a look at it. Okay, so we're writing some kind of broken 7-segment display decoder, which is a very weird one, but yep, okay. We're doing this. Let's grab that test input and let's go and bring it into our test. So that is our input here. Same format that we're getting it here. Okay. So task 1 is a lot easier than task 2, but I'm going to try and build the input in a way where doing both of them is possible. So what we're going to do is we have got a vector of displays. I'll call it a display, a segment display, a segment or segment display info, better name. So segment display info has two parts. It has the full cycle, which is full cycle, which is a vector of, okay, we're going to need to make a new string type for this. We're going to make an enum segment wire, and in that we are going to have A, B, C, D, E, F, and G. And then we're going to have a segment instruction, which contains a vec of segment wire. And then we're going to have a segment display info, which first has a vector of segment instructions, and then has an output, which is also a vec of segment instructions. Ooh, okay. Then this here, our segment instruction is wires this. And this is a struct. And then this here is our segments, let's just call it. Okay, so that is our full output model that we're going to try and get to. Ooh, okay. Let's start with the easy part. The easy part is we're going to need nom combinator value, and we'll say let A is equal to value segment wire A, and we're also going to need character complete car A, B, C, D, E, F, G, B, C, D, E, G, B, C, D, E, F, G, B, C, D, E, F, G. And it has just occurred to me that wires, a segment wire, this segment instruction actually can use a B tree set. Which will give us some slightly nicer operations, provided that we derive copy, clone, ec, partial ec ord, partial ord on these. Okay, so now we've got those. We can say let wire, let segment instruction is equal to a, and we need to bring in parser up here to get access to everything we want. So this is equal to A, or B, or C, or D, or E. You know what? Actually, let's inline these, but we'll inline them using REST Analyzer. A or B or C or D or E or F or G. So those are our legal segment instructions. Okay, so now we have our segment instructions. We can say that a so that they're actually a segment instruction, a segment wire is a many segment wire. And in fact, it is, if we can map this, we can say map segment wire i.into_iter.collect, and that is going to let us map our type into whatever we want. In this case, it's going to be a B-tree map, or a B-tree set even. And then we need to say that a segment instructions is equal to a separated list one of space and segment instruction. Separated list one for that, of course. Which is in sequence, is in multi as well. It is, okay. What doesn't it like about separated list one, the way I've added it there? It's the comma I'm missing here, it doesn't like. Nice, perfect, okay. And we're also going to need separated pair. We can say that a segment display info is equal to a separated pair of segment instructions space tag space pipe space segment instructions, which let's try using then style instead of separated pair. It's just more expressive. So we are looking for a segment instruction, then a tag space pipe space, then a segment instructions, and we're going to say let segment display info is equal to map that, and that gives us full cycle and not then. And of course we need to bring in bytes complete tag. There we go. And now A, what is A? Okay, so we have got, I think it should look like this. So first thing we have in here is our full cycle, then something we don't care about, and then our output. It does, yep, that's correct. And then that is going to get mapped into a segment display info of full cycle and output. Okay, and then we want a separated list one which uses the line ending from in here. And we will say that our parser is mute parser is equal to map separated list one of line ending and segment display info as segments into parsed input segments parser.parse on input. Okay, it is not happy about this. What does it not like here? Type of segment instruction. How do I read more? Select type of value segment instruction. Of course, because this here needs to be mapped into a segment instruction. Map this as a wires into a segment instruction of wires. Okay, expected segment instruction, found segment instruction. Oh, okay, hold on. It's this one here that needs that map applied to it. This is segment instruction of that. There we go. This is the wires field. Perfect, okay. And it's now just complaining that segment instruction is moved, so we need to make it copyable. Dot I. Really? It just needs to be mute. Ooh, okay. Segment instructions moved and used after move cannot because it's an if and mute, which does not copy. That's why doing this should fix that. But of course segment wire now also needs to have that treatment to it, of course, right? I see. Pass I. And now let's inline each of these. Okay, and now do we have any errors? Use of moved value segment instructions. segment instructions also needs to be now I'm second guessing myself. Yeah, this is all going to need to be okay. If anyone knows a way to avoid that, please let me know, because that's really ugly. But hopefully this should now mean that if I go and I attach some debug derives to all of these, and then we call debug on task 1 on input, and we say in our test that we want to assert task pass task 1 test. Test failed, but interesting, did not pass. Parser failed at a car. BE, new line. Oh, it's because I forgot to trim. That's my bad. That looks good to me. Cool. Right. Okay, so what task 1 wants us to do is count the digits in the output values that use a unique number of segments, which means 1, 4, 7, or 8. So the easiest way to write that is to say input dot, so this is going to be okay, input dot segments iter dot map segment dot output iter, and we'll make that a flat map, and then we'll say map, and then we can just say segment dot we'll say iter, and then we say map wire dot wires dot len. Then we want to filter n, where n is equal to 1, or n is equal to 4, or n is equal to 7, or n is equal to 8. And then we want to count. And this is going to be a usize, and this is going to be a 26, apparently. Missing a closed delimiter. You are closed at the end of the flat map, you are closed there, you are closed. I'm not closing the OK. Ooh, still doesn't like something. You know what it'll be? We might need even a third, and we may have hit excessive levels of ampersand. There we go, just the one. Okay, and let's have a look at that test output. 13, counting only digits in the output values. There are 26 instances that use a unique... Oh, it's not 1, 4, 7, or 8, it's 2, 4, 3, and 9 that we're looking for. Because that's the number of cells in the wire. 2, 4, 3, and 9. Really? Okay. Have I miscounted? One, 2, 3, 4. 1, 2, 3. Oh, and of course, that's not. These are 7 segments. Okay, perfect. So our first test passes, which means that we can get our first value out of it by doing target release util. Run year is 21, day is 8. 274. That's the right answer. And is part 2 going to make us, through a little deduction, you should now be able to determine the remaining digits. Consider the first example above. Makes sense in the following configurations. So the unique signal patterns would correspond to the following digits. Yep. Then the 4 digits of the output can be decoded. Therefore, the output value for this entry is that. Following the same process for each, you get the following outputs. Adding all of them together, you get this. What do you get if you sum up all the output values? Okay, so we need to figure out our process to decode all of these. And this we can sort of just tune by hand, I suppose. It's a very small input set, which means we can take quite a specialized approach to it. So if we think about it, we have. Let's go back up to their example here. So the intersection of. Okay, so 1 tells us. Okay, so C and F are the hardest to decide between initially. We have no way of knowing between C and F, but we do know a way of finding A, because A is the whichever one we find has 3 wires in it, subtract whichever one we find has 1 in it, has 2 in it. And that will tell us which one is A. We can then use that information of which one is A. What does that give us? That gives us, from what we know, so that tells us that given that we know A, we can find G, because oh no, because it could be D. Oh no, we can do 4 plus A, and then that gives us this shape here, and then only one of the ones with 9 will have 1 left over, and that gives us G. Okay, so there's lots of different. There's quite a few different ways to solve this, I think. Actually, how do they do it? Unique patterns would correspond. AB is 1. Okay, I see, yeah. Okay. So basically we just need to assess what we know at every stage. We have a set of numbers that could correspond to sets of wires. I'm trying to think of a way if we can do this without just hard coding a solution, but I actually think hard coding a solution might be more elegant here. So what we can do, let's just do this in a little let's just do this in our comments here. So we can say, knowing that we will call this A, B, C, D, E, F, G. Okay. First, CF. Okay, so first A. We have the following buckets. So we've got 1, 2, 3, 4, 5, 6. 6 is 0. N and V, so 6 is 0. 2 is 1. 1, 2, 3, 4. 5 is 2. 5 is 3. 4 is 4. 5 is 2 or 3. 4 is 4. 5 could also be 5. 6 is 6. 6 is 0 or 6. 3 must be 7. 7 must be 8. And 6 could also be 9. So these are the number of possible segments that can be on. Okay, so for 2 segments we know it's 1. For 3 segments we know it is 7. 4 segments we know it is 4. For 6 segments it is 0, 6 or 9. For 5 segments it is 2, 3, 5, 0, 6, 9 and then 8. Okay, so that is our full grouping. Okay, known initially. 1 has only 2 elements. 7 has known. 1 has only 2 elements, it is found. 2, how can we relate 2 to everything else? So 2 is just a 2's easiest relationship. Does 2 have any easy relationships? I'm looking at the things with dlit. None of them. I wonder, is there any of them that use a unique segment? Off, no. I'm looking to see if any of the segments are only used by. Well, let's come back to 2. 3 and 4. Oh wait, 4 has only 4 elements. It is segments. 4 has exactly 2 elements. Okay. 5, we don't have an easy way of knowing. 6, 7 has exactly 3 segments. It is found. And then 8 has exactly 7 segments. It is found. Okay. So now what we can do is we can say that so A is easy to identify at 7 minus 1. Are there any other fun things we can do? We can identify B and D by subtracting these, by doing 4 minus 1. This gives us D and B. Just looking at what we can build out of the ones we know. Okay, I'm gonna have a pause and figure out the mapping, and then I'll get back to you. Okay, so we have a nice easy one for figuring out 6. So let's look at these. So if we take 8 and we want to get to 6, that means we need to isolate this position here and turn it off. But I just saw how to do that in my mind, but I may have gone insane. We don't have a way of isolating C without F. Okay, never mind. I've gone insane. We don't have a way of... Alright, the set subtractive approach isn't going to work, but I think I've come up with a better solution. So what we know is actually... we know 0 is equal to, and then I'm going to normalize it to A, B, C, E, F, G. 1 is equal to CF. 2 is equal to A, C, D, E, G. 3 is equal to A, C, D, F, G. 4 1, 2 is B, C, D, F. 5 is A, B, D, F, G. 6 is A, B, D, E, F, G. 7 is A, C, F. 8 is A, B, C, D, E, F, G. 9 is A, B, C, D, F, G. A, B, C, D, F, G. So those are all of our legal, that is all of the things that are in there, right? So what we can do is we can rule out permutations by basically generating we know that the wires are crossed, right? So we can generate every way that every permutation of A, B, C, D, E, G, and then we can just try them and see if those permutations give us all of these possible outcomes when we run them through our our permutation converter, if that makes sense. So we're actually going to give these a repr, which is very rare for me. 0, 1, 2, 3, 4, 5, 6, and we're going to say repr is U8 because they're very small. Okay, so now what we need to do is we just need to generate our mappings, and our mappings are just going to be based on indexes in a list. So we can say let mappings equals 0 up to 6 dot map n as segment wire dot permutations okay permutations 7 non-primitive cast I yes, so we say Yeah, this should work. I'm just trying to think, because we can check a permutation's legality by whether or not the permutation generates all of these. Right. Let's define some numbers. Const nums is we'll say let nums is equal to a vector of vectors, but let's start on our first one. I'm going to say use segment wire. It's a very pollutant namespace, so I'm going to just scope it a bit more inwardly. So we've got A, B, C, E, F, G, C, F, A, C, D, E, G, A, C, D, F, G, B, C, D, F, A, B, D, F, G, A, C, F, A, B, C, D, E, F, G, A, B, C, D, F, G. Now, even better than that, each of these can be a B tree set from iter of that. Yes, so let's do that. Okay, hold on. B tree set from iter. Okay. Nice, okay, so we have a vector of wire sets. In fact, yeah, so these are the same as each wire. Okay. So what we need to do is we need a function called a permute map, which takes in a map which is a vector of B tree of segment wire. So really, it takes in any sequence segment wire, and it takes in an input, which is a B tree set of segment wire. And it produces a new B tree set of segment wire, and the way it's going to do that is by saying that input.iter.copied.map, and now we want to, so this is going to be 0, 1, 2, etc. So we say n as, let's say that this is repro usize, just to save ourselves a conversion. N as usize. Into the map. Filter map. N as usize. N.get. Yep, that works. Collect. Of course, and then we need to do our reverse map. G. So once we have our target in the map, I see the actual problem here is this needs to be copied. Okay, so that there is a function that is going to let us try a permutation on a map. So I don't even know that this will be needed. All we need to know is that our final result has no, this is our target map here. So we'll say is legal permutation, and so we have a map of segment wires. We have a permutation, which is a vec of segment wire, which is a vec of no. So our permutation map. Yeah, let's call this on here our permutation, just so that we have legal permutation segment wire. And then here we are looking for a map of, they are called segment instruction. So this is our test. And we want to check if that permutation gives rise to legal. Okay, so now we say let nums. So this is what we want to find. And you know what? This here, this can even be a B-tree set from iter. These, and this here is use segment wire everything. Okay, so this gives us our nums, which is a B-tree set of segment wires. Now we need to generate that by saying test.iter.map wire.wires, and we want to call permute-map permutation on those wires to get a new B-tree map. And then we will collect that, and we'll say let permuted map, permuted test is equal to this, and this is a B-tree set, of course. And now we can simply say nums equals permuted test. So this is going to tell us yes, so this is going to tell us if our nums is equal to our permuted test, and if it is, then we have a legal permutation, and we now know all of the mappings. We simply need to apply those. Yes, okay. So now what we can do is we can say, we can build a decode function. And I'm going to just like function nummap this. As a vec btree set segment wire. There we go. So now our decode is going to take in a permutation, which is an instruction for how to decode it. And it's going to take in a value, which is a segment instruction. And it's going to produce a size, because we're using array indices. Okay, and so now what we do is we say permute map permutation value.wires, and that gives us a sort of hopefully that should convert it back into a decode map, into a decoded map. Right? Oh no, because they're not just swapped, they're rolled forward. So what we need is an unpermute map. No, this is fine. Decode map is already doing that operation. And then we can say nummap.iter.find find position n where n is equal to value unwrap is equal to decode map. I still can't spell permutation. Nummap value. Oh, yeah, yes, nummap will be ordered. Wait, yes, nummap is. What does find position return? Oh, okay. Dot zero. And cannot find map. That is because map is called here permutation now. Cannot compare btree set. You can if I put some ampersands on this side. Okay, perfect. So now we should have everything we need, and I just need to glue it together properly. So if I can manage this, we should be able to say, okay. Ooh, okay. And we'll say segments is going to just return, is going to return a vec of every segment. Wire. We're going to say segments iter dot into iter dot permute dot permutation. Snippet engine is not configured. Permutations of 7 dot map n. So n here is going to be a vec of segment wire, so that's our permutation. So first we want to filter it and say is legal permutation, and we need to do this for input dot info. What's the term again? It is input segments. So what we want to do is we want to say ask to here input.segments.iter.map segment, and now a segment let's just get all of our brackets right now. Is legal permutation is going to have brackets, then we're mapping it, and then we are okaying it, and then here we are going to say sum. That's what we need to work towards. Okay. Okay, so is legal permutation takes a permutation, takes a segment dot wire. Permutation. Now each segment here is a segment display info, so this is full cycle. And this is going to return a usize. So now that gives us a now that we have a filter, we now have a valid legal permutation. We should say map and map permutation to decode permutation with segment wire. So now this needs to be each digit of the output. Okay, yes. Okay, so hold on. So inside our segment we can say let decoded equals, and we're going to filter map here. Next. Okay, so decoded here is a segment, is a permutation. So this here is our permutation, found by checking for legal permutations. Okay, then with our permutation, we need to say we need to flat map actually. To like filter flat map, which is very silly. Yes. Okay. So we've got our permutation, and so now with our permutation, we need to say segment dot output. I've called it. Right, segment output, yeah. Iter dot falls, and our power is going to start off as 0. And we're going to sum, and we have got power and segment. So we are going to do 10 to the power of p times by so this needs to go in reverse so that we go from least significant to most significant, times by decode permutation segment. Ambiguous numeric, right. To usize. Expected U32, found usize, okay. U32 then. Change this to a U32. Cannot multiply U32 by usize. 10 to decode. Decode is returning a usize. To stop doing that. Let's just convert it into a U32. Decode as U32. Our segment needs to be passed in like this. No, our permutation. Oh wait. Decode expects. Is decode expecting ownership? Decode, you do not need ownership. You by no measure need ownership of this value. But permutation does need to be passed in like that. Some exists for U32, but it's not. Oh, we don't need to sum because we're folding. No, map. Yes, do that. We need power. This needs to be scan. And then you say how does scan work? Scan, similar to fold that holds internal state and produces a new iterator. 1, 2, 3, scan 1. State, the state is mutable and you return the new elements. Wonderful. So the state is mutable, that's our segment, so that's our power. So we say star p plus equals 1. And then to just save ourselves the hassle, let's just work on p minus 1 here. Wonderful. And scan can fail, so we will just say, sum. Lovely. Expected integer, found and mute integer. Oh, p. There we go. Lovely. Okay, now what does it not like? It cannot infer that this should be summed to a U32. Does that work? Is that the task? Task 2 should give an output of this number here. I'd be very surprised if it did pass. I'd be happy. It would be unexpected. Sums to 0. Of course it sums to 0. Why does it sum to 0? Because we're doing 2 to the p minus 1, 0, 10 to the 10 times by decode. U32, sum. I'm guessing that the decode is what's messing this up. We'll look at those decoding values. Oh, interesting. And we never get to decode. Do we not find a legal permutation? Does this just output false? It does. Interesting. Okay, so is legal permutation never resolves to true? Whereas you would think with some permutation it would. We would find some permutation where we can find all of these values by permuting. Let's pre-allocate our permutations. And now in here we can simply say all permutations iter. And let's quickly look at all permutations just to check that it has sort of the borrow view borrow. It's not being moved. Don't move that here. Expecting. Yeah, so it just has every single possible permutation. Okay. None of those permutations are legal, so it must be in our is legal permutation. It must be in our permute map that something ends up being wrong here. As you would think, one of them must produce, one of these inputs must be illegal to produce the permutation we want. So it must be permute map that's broken. A goes to we get n from our permutation. Get our input as usize. Oh, that's wrong, I think. We want to say here, we want to say that for every element in our input, we want to find its place in the permutation. We want to find the position of where I is n. Different algorithm. Does this one work? Fingers crossed. Get a sum eventually. Nope. Is this ever returning true now? I guess is the question to ask. You know, it doesn't look it. Nope, none of these are true yet. The goal is for every value in our test to be mapped to a unique value in here under some permutation. We just need to find out what that permutation is. So it is the permute map that must be wrong. Let's just test permute map individually. So if I were to say debug, and then we'll return immediately after that. Debug permutation is so our permutation is going to be, let's look at the one that they have here. The one they have here is DEA FGBC. That is our permutation, and the hope is that that can turn ABCDEF. We want to do decode permutation segment instruction wires vector into iter collect. And then the wires here, let's look at, for example, ACEDGFB. ACEDGFB. It's just Rust Analyzer getting itself confused, no? Oh, it's because I've said the word permutation here like some strange person. What do we get out of this? Seven. It's an off by one error. There's an off by one error, which means we're introducing lots of timesing by 0. Decode +1. Well, that was it. But this will now give us 8 as we expect it to, yes. So that correctly decodes the value 8. If we give another one of these, FBCAD, and we decode that, we get back 4. FBC AD is not 4, FBC AD is... So maybe our decoder doesn't work. FBC AD should give back 3. A, B, C, D, E, F, G, that's correct. 0, 1, 2, 3, 4, 5, 6. No, 1. This is not correct. 0. A, B, C, E, F, G. No, it is. 1, 2, 3. Should be giving 3. Okay. 3 should give back A, B, C, A, B, C, D, F, G. A, C, D, F, G. A, C, D, F, G is 3. Yes. Okay. Why do you decode to 4? Let's print out what the decode map goes to. So our permute map of that gives us A, C, D, F, G, which should be a 3. It is 0 indexed. This should be 3 would be correct here. What went wrong for the first one then? First one came back as a 7 somehow. A, C, E, D, G, F, B, A. So why are you a 7? Am I missing a number? 0, 1, 2, 3, 4, 5, 6, 7, 8. I'm missing a number. That would certainly do it. Which one am I missing then? A, B, C, E, F, G, C, F, A, C, D, E, G, A, C, D, E, G, A, C, D, F, G, B, C, D, F, A, B, D, F, G, A, B, D, E, F, G. A, B, D, E, F, G. So that now correctly gives us an 8 there. Okay, nice. So we know our decoder works. I don't suppose that's magically fixed our test. I would be very surprised if it did. Oh, and we won't get an output if we're debugging constantly. That was it. That was all that was breaking it. Oh, that's very annoying. Well, I found it eventually. And it is very slow, but it does get there in the end. And tests run in debug mode as well, whereas target release util run year 21 day 8. I suspect might be quite a bit faster. This number here. is the right answer.